Let's get started. So let's see. So welcome back from Thanksgiving, everyone. Hopefully everyone had a had a good break. I guess we didn't change the schedule for this class, but two lectures left in the semester. I know it's almost coming to an end. The last two lectures, we're going to talk about some really cool stuff. So hopefully it keeps everyone engaged as we finish up this semester. So far in this classification section, we've talked about techniques for some linear classifiers, and these linear classifiers are great for understanding what's going on. They're so useful in kind of and actually work great in very high dimensional data, but they're not the most powerful type of classifiers. They're nonlinear classifiers, and so the next couple of lectures are going to be mainly about those. The first one we're going to talk about are going to be the support vector machines, including with kernels. This is kind of a fairly direct generalization of the linear classifiers. And then in the final lecture, we'll talk about some more kind of different ways of doing this, including a very brief introduction to neural nets, which is kind of what a lot of the deep learning is. So I'll try and give perspective onto what is going on with deep learning through this lecture. And so the perceptron, which you talked about last time, will actually play a role within some neural nets. So it'll have been useful to have understood that as well. So let's quickly look at the schedule. So again, we have these two lectures left. I postponed a lecture around the time of the election. So I usually have an end of the semester review during one of the lectures. I'm going to do this in the Monday after classes end. I know this is during the time for exams. You might have an exam on that day, so I'll plan to put this on YouTube also. Unfortunately, I originally planned to do it at the regular time, but there's a PhD thesis proposal that I had scheduled that overlaps with that. So that ends at 2. So I'll plan to start this at that around 2:15, and then we'll be about an hour and a half or so, and I'll plan to go through this practice exam. You can find it down there. That document is longer than what the exam will be. It's kind of a superset of questions. Look at them. If you can do well on those questions, you're going to do great on the final exam. I suggest you go and look through, try and solve them before the review session, so then you can try and do them, or before you watch it, so then you can see how it's done after you've tried to make an attempt. Also, homework 5 is posted, and so start working on that. It should not have, you don't need to use Python or any programming for that. It might be useful for the first question because you're going to do some calculations, and that's probably the easiest way to do it, but it's not required for this assignment. Hopefully it's a little bit lighter than the last few. I know the end of the semester is a busy time. And then today we have quiz number 6, our final quiz. We'll stop the lecture today at 2:30, and we'll jump into that. That quiz will be open until midnight. And you'll have one sheet of paper. You can turn it again, and you'll get 5 bonus points. So last quiz number 5, a bunch of people didn't do that. They left some points on the table. I recommend you do that, if not just for studying, because everyone else in the class got those points. I would assume you'd want to as well. Okay, and then the final exam will be Friday. Oh, what lectures does Q6 cover? It covers quiz 6 will be on all of clustering and the previous 2 lectures on classification. It will not cover the stuff in today's lecture, although we'll talk about some stuff today which hopefully will further your understanding of the first 2 lectures. So, but I won't ask you specifically about SVMs or kernels on this, which will be the main topic of today, but we'll, review some aspects of it that which hopefully are going to be useful. So clustering and then the first 2 lectures of classification. Yeah, okay. So then the final exam, our exam date scheduled by the registrar's office is Friday, December 11th, and from 1 to 3 p.m. Okay, so how I'm going to do this? I'm going to do this I'm going to do the final exam implement as a big quiz on Canvas. I haven't created that in Canvas yet, but we'll post that soon. And I will make it available in the morning on that day and close it at midnight. Okay, so you're going to have all day to do it, but you'll once you start, you'll have 2 hours like the regular exam time. And I recommend you do it from 1 to 3 p.m. During that time, I will be on Zoom and able to answer questions. Otherwise, you can email me or the TAs or send us messages on Canvas, and we'll try and get back to you as soon as possible. But we might not be able to during the 2-hour window you're taking the exam. Yeah, so I'll try and be available, but I can only totally guarantee it between 1 and 3 p.m. on those days. I'll be on the same Zoom link that we're on now. Great. So any questions on the rest of the schedule? Oh, for the final, you'll get a chance to turn in again a cheat sheet, and you'll be able to get some bonus points towards your final grade on the exam, just like on the quizzes. I'll say you get 6 sheets, so you could turn in the same 6 or 5 or 6 sheets you use for the quizzes for this. That's kind of the idea. If you thought those were useful, then you probably already have them. If you want to rethink those, and that's probably also kind of a good idea. The exam will cover everything in class, and it will be similar to kind of 4 quizzes all stuck together. Okay, so that's going to be the idea. Great. So again, we'll continue office hours through this week, and then probably on demand. Maybe I'll probably try and do them the day before the exam, also on Thursday. I'll post on Canvas to clarify that. Okay. So this lecture today is going to be on support vector machines and kernels and how to think about these nonlinear sort of classifiers. Okay. And right, so to review classification, okay, so this is a supervised problem. So the input here is going to be X, which is going to be a subset of RD. Okay, so endpoints in RD, X1 up to Xn. And we're also going to get some labels Y in Rn, non-Rn in -1, +1, n. So we're going to get, for each data point, it's going to be associated with a -1 or +1. It's a label, and we're going to try and classify this into 2 sets. Okay, so their version of this that do multiple classes, turns out they're fairly similar to kind of the main techniques for just 2 classes. Okay, and the goal is going to be a function g that goes from RD, which is the same space as the input, to R, right? So not to -1 or +1, but so g of xi is going to be greater than 0 if and only if yi is equal to +1, and otherwise it's going to be the value be less than 0 if the sign, associated sign is negative here, right? So we're just going to use the sign of this function to do this classification. Okay, and so up until now, we've focused on these linear classifiers. Okay, so you had these plus points and these minus points, and you tried to find a linear classifier, right? And so this corresponded with a function, right? We could describe this by some normal direction, and then there's some offset, and so the function is going to be positive in the direction that w is pointing, and negative on the other side. And if it's a linear function from Rd to R, then this separator has to be a line. Okay, but if we also, if there's also something like if we added some more data points here, right? So now this linear function is not doing so well. It's misclassified a couple of the points here. Okay, so and it looks like there's no linear function I can choose that is going to completely separate all the positive points from the negative points. If I look at these 2 points that are misclassified, and if I were to try and switch this, kind of change the direction of this line, I couldn't ever perfectly classify all the data points I have. Oh, if we go to R3, which are gx become a plane, or does it stay a line? Yeah. Well, g of x is a function from Rd to R, right? So it's, now what you're asking is, this line here are the set of points where g of x equals 0, right? This separator line, the geometric object, which kind of you think of as separating the points, this is going to become, when I'm in R2, this is a line. In R3, that's a separating plane. It's always d minus 1 dimensional. All right, so this subspace, this is going to be d minus 1 dimensional. Okay, and it's going to be a subspace if it's a linear classifier. It's going to be a linear subspace, like we talked about with PCA, right? It's going to be, think of a rank K or d minus 1 kind of subspace is what separates these things. Today we're going to talk about when the decision boundary is nonlinear, right? So what we're going to want now is a function that looks like this. Okay, so now if I can draw a function that looks like this red curve, right? This is where g of x, we'll call this g of x prime, I guess, right? Where g of x prime is 0, this can be a non-linear function. And now I've classified all these points correctly. And the hope is, well, this function isn't too wild. You know, if I had more data points, this probably, I would guess, does a better job of predicting new data points than this linear classifier. Okay, so I've done a better job of kind of classifying with this non-linear function. Okay, with the green one, I had to have it basically represented by a dot product in this normal, but now I can't represent it that way. I somehow need to learn a non-linear function now. Okay, so today's lecture will be kind of trying to reuse the same machinery we had before and tweak it a little bit to something called a support vector machine, which is going to be able to learn these non-linear types of classifiers that still look pretty, you know, they still make sense to draw. We're going to look at ones that are going to be described by a polynomial, and also ones which are going to be described by kind of the, I guess, the level set of a kernel density estimate with signs in it. So they're both kernel like Gaussian kernel sort of classifiers and these polynomial classifiers. Okay, so that's the goal of today's lecture. And again, we'll want this to generalize to new data well, because we have a supervised problem, so we should be testing with cross-validation to generalize to new data. Okay. Okay, so let's start with this idea of this, remember, for linear g of x, right? So this was, then we're going to end up having this function be x, a dot product with w plus some offset b, where this w was this normal direction. Okay, so we're still going to keep, this idea of this offset. We're going to keep this idea of having this offset. This is fine, but what we're going to do is we're going to replace this notion of the inner product, right? So for linear x w, remember, you know, just to be clear, this is 1 to d of xi dot, so, or times wi, right? Where we had this wi representation of the model, right? So the model was represented by the b and the w, right? So the w is our representation of the model, and we just multiply each coefficient by a single, or each variable of the d variables we have in our data point x by a single coefficient. So this is a linear function. Okay. The key thing we're going to do is we're going to look at, let's not highlight that one. We're going to look at this inner product, and we're going to generalize this to nonlinear inner products. And then we'll see through the lecture today that if you're careful about it, you can get all the same machinery views so far to work with certain types of nonlinear inner products instead. So we're going to replace x dot w with, we'll do, say, x w with a kernel, like a special type of inner product instead. And so we'll use 3 types of kernels. So we'll use a Gaussian kernel. I'll just write these down as examples. Then this one will be, remember, the Gaussian kernel, or basically the Gaussian distribution. This is showing up again. I guess it's probably the last time, or almost last time it's showing up, which is basically the Euclidean distance between x and p squared divided by the some bandwidth parameter, sigma squared, the standard deviation, normalizing it, and it's all to the e to the negative that power, right? So this looked like a kernel that looked like this. There's a similar, so the Laplace kernel is similar and sometimes used. It's actually a little bit simpler. Sorry, I don't know why I'm using p here. This is w minus x not squared divided by sigma. Okay, and the Laplace kernel looks like this instead. It's kind of pointier instead. Okay, and then there's the polynomial kernel. And this one is written as the inner product between w and x plus c, and this is kind of representing the offset inside of here up to some power r. Okay, so I can basically always set c equals to 1, just a 1 parameter here, and so okay, so these now have, I can use these kernels instead of the linear inner product, and we'll see today how to make kind of classification work, and these will give rise to nonlinear boundaries in this of these so decision boundaries. They still have a parameter. This sigma or this r somehow is still controlling how complex this is. So like in polynomial regression, and there's a version of kernel regression as well we didn't talk about, these, as I make r bigger, I'm getting a more complex model here. So this is equivalent to looking at all kind of polynomial expressions, this bottom one, in place of a linear thing, a linear function up to a power r. So if I make r equals 2, I can get a quadratic, or a quadratic curve. If I get it power 3, I can get a cubic curve that is this red decision boundary. Right, so I need to increase this power r. The more I increase it, I get a more complex curve. With the kernel, with the exponential families of kernels here, the smaller I get the bandwidth, the more complexity I get. So as sigma gets smaller, I'm allowing more complexity in the model in some way. So I can overfit by making these models too complicated, similar to the form of regression here as well. So I should be careful about how I choose these parameters. So, okay, so let me try and illustrate. All right, so let me kind of first give one view that's not really the kernel SVM view, although it's basically equivalent to what how a kernel SVM is working. Okay, and that's to use the same trick we did for the polynomial version of regression. I can do a kernel expansion. Okay, so what I can do is I can do this feature expansion, as is often called. I'm going to map a point P in our D to a point Q in, what is this, in R, what is it, like something like O of D to the power R, right? So to a much higher dimensional space. Okay, and so basically this map from P to Q is going to be equal to kind of this vectorized form of this, where I can think of the first coordinate Q1, and I'll do an example where P is equal to P1, P2, right? So this is in R2. We're going to map this up to a 5-dimensional space. Okay, so the first coordinate is just going to be P1. The second coordinate is just going to be P2. But then I can also get these other terms. Say Q3 can be P1 squared. Q4 can be P2 squared. And Q5 can be P1 times P2. Right, so now this is an element of R5. Okay, so I've kind of mapped it to a higher dimensional space, right? A similar way I did an expansion. I think for the regression, we only looked at a 1-dimensional value, and we did an expansion this way. And there's also going to be an offset, right? There's also this offset term B, so there's also this constant 1. I've left that off there. And so I can map these points into this higher dimensional space by just expanding it. And now my model is going to be instead of W, let's call this alpha in R5, which is going to be alpha equals alpha 1, alpha 2, up to alpha 5, right? And each of these is going to correspond with the coefficient to this corresponding new variable, right? So I'm going to get a polynomial expression for this multidimensional point, and then I can solve it the same way I did before. I can solve it as a linear function once I've done this expansion up to a higher dimensional space. Okay, and so I will just kind of want to give you a picture of how this looks like, of why this is a nonlinear separator now. Let's draw this line. Okay, so let's say that this is just going to be R1. Okay, and I'm going to have some sets of points here. Right? Okay, so I've got the negative points in the middle and positive points on so either side. Right? So I could try and solve this, or if I go back to this picture where I can't find a linear separator, I can still find a good green curve with an SVM, and it penalizes it, and my total, I don't get zero misclassification, but I get some sort of penalty. It's kind of okay, right? But I might rather get something that's a nonlinear boundary. Okay, so I've got these points in R1. I can't, and in this case, there's really no good linear separator. Some cases, there might be an okay linear separator, like the green line before. It only misclassified a couple points. But this one is so not doing so well. Either I have to misclassify almost half the positive points in either way. So it's probably not a good model to use a linear separator. Okay, so let's pretend we add another coordinate here. Okay, so this is R1. So each of them has, say, an x value, x1, x5, x6. Right, there are these 9 data points that each have a one-dimensional value. I want to do this expansion, and now I'm going to give them two-dimensional values. So now it's going to live in two-dimensional space instead. So each x, so I'm basically mapping p equals x to q equals x squared. Okay, so let's give a sense of what this looks like. Every point then needs to lie on this parabola. Hopefully, let me try and draw the parabola a little bit fatter so that I can actually draw it. Okay, so I'm going to draw the points on this parabola. And so what this does is it maps every point up. Let me try one more time drawing this. Okay, that's maybe not quite what a parabola looks like, but this will help illustrate what's going on. Okay, I'm going to map each of these points up. So let's say this point was -1. Well, now it's going to be at, or let's say -1/2. Now it's going to be at -1/2, 1/4. Right? That's the value of this point here. Right? -1/2 squared is 1/4. Right? This one is maybe -1. And so this is going to be something like, or -1, 1. That's the value of this point. This one gets mapped up to here. This is now, let me draw this. Let me draw these in green. Okay, and then yeah, these will be in cyan. Sure. Okay, great. So now, now I've lifted them up to this higher dimensional space. Now they all lie in R2, right? All of these lie in R2. They're now this higher dimensional space I have available. And it turns out I can now find a nice linear separator in between these points. I can separate the, let me draw this on a weird angle, right? So now I can find a line. This was supposed to be a line here that is going through these points. I can find a line that's separating the positive points from the negative points. In R2, there's now exists a linear separator. But if I map this down into where are the points assigned a negative label and where are they assigned a positive label, like this. This is now nonlinear, right? The left and the right side are assigned a positive label, the inside a negative label. So in the original space, it's nonlinear, but in this lifted space, it becomes this linear separator. So I can lift them up to a higher dimension by expanding it into a higher dimensional point, right? This is now an R2. And then in that space, I can often find a good linear separator. Okay, and if I were to map this function back down into the space, the actual function g that I'm predicting is going to be this nonlinear function, and its decision boundary is going to be at these 2 points are going to be the decision boundary of the separator. In 1D, it looks like 2 points, right? But if I could draw the picture starting at 2 dimensions, going up to 5 dimensions, it's going to be this kind of curve through the space. Okay, so it's going to look something like this. Although I guess it can't be this complicated. This would require at least a cubic, so at least a third power, expansion to the third power in order to get something that curves like this. Okay. Okay, so this is kind of the idea of this expansion. I want to mention that there are ways to expand kind of these other kernels, the Gaussian and the Laplace kernels to R, let's call this M also. So I can go up to this m-dimensional space for these Gaussian and Laplace kernels as well. But this is more complicated. In fact, M for, so I can say for, if I want to do this exactly, M needs to be actually infinite dimensional. So you do this infinite dimensional function space, which is kind of weird, but I can do a, this approximately. And then I'll say M greater or equal to like 100. I can go to about 100 dimensions and I can do a pretty good job of this. So using this approximate feature map to a high dimensional space. So there are ways to do this with these other kind of centrally symmetric kernels, but these are a bit more complicated. So they aren't that complicated, it turns out, but we aren't going to talk about them in this course. Okay. Okay. So instead, we're going to deal with these other sort of centrally symmetric kernel or radial basis functions. They're sometimes called these RBF kernels in a different way using kernel SVMs. Okay. Okay. So we're now going to think of, we're going to do something called the Kernel Perceptron algorithm. And we're going to think about this through something called the dual mistake counter. Okay, so we're going to see that we can actually implement the perceptron algorithm using one of these other kernels, using kind of the Gaussian function in place of this linear inner product. And things will still work if you kind of change a little bit how you represent the data. And this change of how you represent the data is going to be called a dual. It's kind of like taking the transpose of a matrix, right? We went from if we're going to go for something like the rows of something, meaning the data points and the columns, the dimensions, to switching that around. That's what we're going to think of when I say a dual. It's going to be some sort of transformation of the data. Okay. Okay, so if we remember the perceptron, the goal was this model, which was this vector W, right? We had here, we assumed it was going through the origin. So the classifier was going through the origin. So we only had negative and positive points, and they could be separated with a half space that went through the origin with no offset. And there was some normal direction. And this was actually not here, but was actually a kind of this vector W, right? And this was kind of, and we got this vector W in particular by a sum of these data points, right? It was a sum of the vector representation of the actual data points we had, right? So this was somehow a sum, I equals 1 n of their n data points of these xi, and we multiplied each data point by its sign yi. We added it if it was a positive one, or we subtracted if it was a negative one. That's always what we did. And there was some alpha I in front, right? And this alpha I told us how many times we added that point, right? So now this representation, this alpha I was representing the number of times we added xi, or actually yi times xi, right? So the number of times we added that onto this model. No, that didn't work. Okay. So these are so we're the way to think about this is the number of mistakes at xi, yi. Every time we had a proposed classifier, right? And we made it, and we realized that this point xi, right? Let's say this is xi plus 1, right? Every time that we realized this point was misclassified, we added it onto our vector W. We just kept adding these on, and this was how we learned this classifier. Okay, so this is one way to think about this, and it's kind of a weird representation, right? Instead of W was an RD, and alpha, this representation of alpha now, this is alpha 1, alpha 2, up to alpha n, right? This is in Rn. And typically, we're going to have d less than n, right? So now we're counting mistakes. So our representation of the classifier is now an n-dimensional vector. We're representing this as an n-dimensional vector now. So it seems kind of wasteful. And we know that we did some analysis. If you remember that the number of alpha I not equal to 0, that this was less than 1 over gamma star squared, right? That was the margin squared, right? So most of these alpha i's are actually 0. We never add this vector on. So it's a little bit wasteful representation to keep an n-dimensional array around. Okay, we'll kind of fix this a little bit later, or we'll say that this isn't really a problem. Okay, but we've expanded the representation from d dimensions to n dimensions now. Okay, but this is going to allow us to actually do something pretty cool. Okay, so we're going to so let's say we have a now a new data point, so p in RD. Okay, and we're going to want to predict it with the function g, right? This is the function we're using that we found using this process. Oh, sorry, my son has PE class upstairs. He just jumped on the ceiling and spooked me a little bit. Looks structurally sound. We're okay. Okay, and and remember, this was ultimately going to be W dotted with P, right? This is what the form is going to be, so we can expand this out. Remember now, W has this new representation we can use. Okay, dotted with P. But we can actually factor out a lot of stuff from this. So from this inner product, it's a linear operator, so we can factor out the sum. Okay, so this will be I equals 1 to n alpha I yi xi p. Okay, so I've just rewritten this. So this linear function now can be written now as the sum over these n terms. Each one of these, right, is going to be multiplied by the inner product of xi and p. Okay, so p is our data point, xi is one of the data points. So now I have this inner product by itself with the data point, which means I can just replace this with xip. I can put a kernel there instead. Okay, if I think of my function this way, so now, and if I do this with the kernel, this could be the polynomial kernel or say the Gaussian kernel, then I'm going to get a nonlinear function instead. Okay, and if you remember the perceptron, I actually, all I needed to do was to check this function on one of the data points I have and check if something was misclassified. I didn't need to use the linear property of it. And then I need to update it with this sort of mistake counter, right? So I can just update the number of mistakes I found here again. Okay, so I can run this same algorithm. Okay, I can run the same algorithm. The kernel perceptron now, let's rewrite this. Okay, I'm going to use a general kernel function, xp. Okay, and so my goal is going to be a function g of p, which is going to be equal to sum of 1 over n of alpha I yi xip. Okay, so this is going to be my potentially nonlinear function. It's still a linear function if I use the old inner product as the kernel. I can still do that, but this alpha I is now going to be, so this is the mistake counter. Okay, and so what am I going to do? So 0, I'm going to set alpha equals to all zeros vector, and then I'm going to say alpha, the first step, I'm going to be say is going to be say 1 for x1 y1 equals to plus 1. So I'm going to pick one of the positive points and set this. This is how I initialized it. Okay, so I'll initialize this, and then repeat if there exists some xi, yi, where g, my function g is now defined as above, xi, let's see, I want to say the sign of this. So the sign of this is not equal to yi, then I'm going to have alpha I plus equals to 1. Right, so I'm going to increment the mistake counter for that one, and that's going to update the function g. right? So this is the whole algorithm, right? So this is the kernel perceptron algorithm. I basically define the function this way with any kernel I want, right? I set one of the positively labeled points as I maintain this mistake counter, alpha I and Rn. All right, now this is in Rn, okay? And then if I find any misclassified point, any point where the g of x function I have gives it the wrong label, then I'm just going to update the mistake counter, and this updates the function g of n, and I do this until it terminates. And now I don't need that. It has to be separable in a linear way, but it can be separable by this polynomial or this Gaussian kernel. In fact, if I set the degree of the polynomial high enough, or if I make the bandwidth of the kernel small enough, as long as there aren't any kind of two x points that have different y values, then I can always find some separator. I'll always be able to find it if I set the parameter high enough. Now, I don't necessarily want to do that. I might overfit and these other things, so you want to do cross-validation to check that. But this kernel perceptron will at some point always work, but it won't give me a linear classifier. Okay, so we've now found a way to solve for a non-linear classifier. Before I move on, let me show you one picture of how to think about this kernel version. This kernel version, I'm going to have these, let's see, these positive points and these, say these negative points here. Okay, let's say these are the points that are in the mistake counter. So what I'm going to think about is having a kernel density estimate where I'm putting kind of a Gaussian kernel on top of each of these, right? So I'm putting a positive Gaussian kernel on the red ones, and I'm going to kind of have a negative Gaussian kernel on these blue ones here. See if I can draw an upside down, which looks kind of like this. Okay, so I'm going to subtract the blue one from the red one, or it's already been subtracted, right? So I'm going to add these two together, and hopefully that's going to give a curve that's going to come down a little bit faster here. It's going to be negative here. Look, something like this. Okay, so now it's going to, and then where is it positive? It's positive here and here. Okay, and it's going to be negative in this range. Right, that's where the green function is negative. Okay, and so in general in higher dimensions, and I think the version of the book you have, there's a picture of that in there. If not, you can buy one in January, hopefully, where it shows a picture of this, or you can find something online. In 2 dimensions, you can see 2 kernel density estimates, and you can see this decision boundary in between. It can be this kind of in 2D, right? In R2, you're going to get something like points like this. So this would be negative, and you can get this kind of cool looking decision boundary here, where it kind of splits the difference between the 2 differently labeled points, but it can have these kind of, it's kind of this fairly smooth boundary, but is not restricted to be this polynomial, something like that. So it can only put bumps where it needs to, kind of adapting this kind of kernel density estimate fit around this data in a pretty nice way. Okay. Okay, so this kernel perceptron, if I can do this representation of this dual mistake counter, right, where I just count the mistakes in this representation of my function, which was just a rewriting of this linear equation. I've just I knew that this representation always had to have this form, right? It was always a sum of the data points in some way. And then if I just kind of expand this form out and factor it out, I get just inner products with each of the data points, and I just replace that with the kernel. And then I just run the algorithm like before, but now I'm doing this dual representation. I'm maintaining this n-dimensional vector of mistakes instead of this this d-dimensional vector of the w, right? So it might be a little bit wasteful representation, but if I don't care about it as an array, I just keep a general list data structure, then that's okay. It's going to be, I'm not going to have to keep track of all the zeros. I can use a different data structure to keep track of that. Okay. All right, this is not yet a support vector machine. A support vector machine takes this to the next level. Okay. The support vector machine says, okay, this mistake counter is kind of limited in a way. Okay. So the support vector machine. Okay, so that's going to, again, look at this model where this W, we're going to think of this W as being the sum over I equals 1. Let's call these actually J equals 1 up to K of alpha J, Yj, let's say kernel of xj dot, right? Because I'm going to be dot, or I'm this is going to be this representation of this. So function. This, I'm kind of thinking about this representation here. I could replace, so I could do something like this kernel expansion, and this could be this Wj representation in, say, Rm. Okay, and if I was able to do that instead for my representation, then I can look at this guy and I can say, in the mistake counter, each alpha j is going to be in 0, 1, 0, 1, 2. It has to be integer which is positive, or it could be 0, so a non-negative integer. Okay, but if I were to optimize this with gradient descent, so with gradient descent, then alpha j can be in the real values. I can have any real value for these alpha j's. This should be more powerful. I'm not restricted to just a positive integer where the sign is already determined for me, right? But I could have a negative value. Maybe one of the positive points, I actually want to get the function just right, I want to make it negative, or I want to make it so it's 1.5, or 0.8342, right? This might work a little bit better. Okay, so I like to make this representation, right? And this is for a model G of P, right? So I'd like to do this for alpha J, Yj, kernel xj to P. I'd like to do it so that this guy can be a real value. I want this to be a real value here instead of kind of just a non-negative integer. Okay, and if it's a real value, I don't really need this y term anymore either. All right, so I can get rid of this y term because I can put a sign into aj, into alpha j. So I don't really need that y term there either. Okay, so this just simplifies this model, this model a little bit. Okay, and so the other thing I've changed, okay, is that I only had the sum go up to k here, or it's so lowercase k. Okay, and I'm not using all the data points. Like I said before, most of the data points often are going to be 0 if I use the perceptron. And so I don't want a model that's going to use all n of these data points. Okay, so I'm going to select a subset. So I'm going to say a subset S subset of X. This will be S1, S2, up to S lowercase k. These are going to be the support vectors. Okay, so these are, I'm only going to use a subset of them to define this model. Okay, so if we remember that we had, okay, if we had points like this and we defined a margin, okay, let's move this point a little bit just for illustration. Okay, if we had this margin here, if this was the max margin separator, we have this kind of this margin around here of the closest points. Okay, so then we can, these points which define the max margin here, then these are what's called the support points. Okay, and so if I want to define this linear classifier, I only needed 3 points, or in general, you need in RD, then a linear classifier has D plus 1 support points. Okay, so if I'm in the case now where I can't have a perfect classifier, and I want to find a non-linear boundary here, maybe I still could have a perfect classifier in this case. Okay, so now I can't have a perfect classifier, so I want to do a non-linear boundary here. Right now, I might need more support points, but I still shouldn't need too many. I still don't really need, let's say, these points over here. These points aren't so important. I don't need to worry about those points. I still probably only need a small number of these points. I probably also need that point, just to be sure that doesn't do something else funny. Okay, so there's still a small number of support points I probably need, and I'd like to identify these. Okay. Okay, but once I have, so this kind of the kernel SVM here. Okay, so basically step 1, I'm going to identify support points as a subset of X. Okay, so how can I identify these? One, I could run, I could run Kernel Perceptron algorithm. Okay, so I could do this with Kernel Perceptron. I could run, I could also choose S equal to X. I could say, let's let them all be support points, okay? Then I could run maybe S equals X plus, I'm going to run some stochastic gradient descent, right? And if I run stochastic gradient descent, I'm only going to, initially I only look at a subset of points. And if I'm doing pretty well with the subset of points, then I can stop looking at the rest of the points, right? And actually, if I remember the hinge loss function, this hinge loss function that I can draw here, right? For this black point, right? It's going to have this z function, z, and it's this one point. If this is xi, its value zi is going to be here. It's going to have some sort of penalty because it's misclassified. But if I look at xj, it's going to have a zj over here because it's going to be classified correctly. And so that means its cost in this hinge loss function, right? Its cost is going to be exactly 0, right? It's going to be exactly 0, and its gradient is going to be 0. So I'm not going to actually optimize anything with respect to this point. Okay, so so even if I run SGD with a point that's not needed in the classifier, then it's still going to stay a value 0. Okay, so I'm going to do this. So I'm going to identify these points, and then I'm going to set G of P equals to the sum over J equals 1 up to K of alpha J of K, let's say Sj, this, right? So this will be S1 up to Sk times P. Okay, so this will be my cost function. And for P, I can actually take the derivative of this cost function still, because I can still compute this function value. And then I just take derivative with respect to the alphas at any point P. Okay, so I just have to compute this value. So I can still define the value zi of a point, right, is still yi times times g of xi, which is going to be yi sum j equals 1 to k of alpha j k of x of xi dot sj, right? So for those fixed support points, I can still, let me swap these around so it's consistent. I'm still going to get sj xi, right? So I can still compute the zi function for any of these points, and I can still plug in whatever the hinge loss function or whatever I want into here. So once I do this, I can still optimize. So then I'm going to optimize over alpha in Rk, right? This alpha vector, this k-dimensional. It started out perhaps as the mistake counter, but then I can optimize these values as well. And so when after I've identified the support points, I can optimize them using gradient descent, and I'm just going to give me a kind of a sparse model, but with any sort of kernel, these nonlinear kernels. So there's kind of a, this is a little bit tricky. I hope the main takeaway you get before we stop for the quiz here is that if I change this, I want to get a nonlinear decision boundary here. I want to get a nonlinear decision boundary. I can do that by replacing this linear inner product, this linear dot product, with the kernel. And one way to do that is an expansion of it to relinearize it to a higher dimensional space, right? Another way of doing that is to keep track of this mistake counter in the kernel perceptron, where I've just replaced this cost function with the linear inner product with the kernel inner product. And this gives me these nonlinear decision boundaries. But this mistake counter ensures that this alpha, the parameters I'm optimizing over, are always going to be so non-negative integers. And so then I can, instead of just restricting them that way and using kernel perceptron, once I've identified a bunch of support points, then I can optimize over these alpha j's with gradient descent, basically the same way I did before. And I kind of were little short in time because we have the quiz today, so I'm not going to kind of work through any more of those details, but hopefully that's enough for you to take away. You know, you can get a linear decision boundary, but it might not kind of classify all the points correctly. Sometimes that's okay. Sometimes you don't want to force it because it won't generalize well, but sometimes you want to get a nonlinear decision boundary, and then you want to use one of these other techniques. Okay, so we'll break for the quiz, and then the last lecture on Wednesday, we'll look at a couple of other very different sort of classifiers, including some neural nets, and see how they kind of fit into this sort of way of thinking. They're going to be kind of a fairly different concept than what we've looked at here so far, but they're going to have some parts going to carry over. Okay, so I'll stop now. The quiz should be available on Canvas, and I'll be available until 3:30 on this Zoom link for any questions you have about the quiz.